have the functions defined as sine of x between 0 and pi, and 0 between pi and 2 pi. And of course, this is 2 pi periodic. And I want to take the Fourier series of it. So, as in the last videos that we did, we will first find the complex Fourier coefficients, and then we will find the real Fourier coefficients using those complex Fourier coefficients. And we will use the tabular method to do the integration by parts of the integrals, okay? Tabular method. So I take my complex Fourier coefficients, so 1 over 2 pi times the integral from 0 to pi of sine x e to the minus I n x dx plus 0. Okay, why 0? Because the integral from pi to 2 pi is simply 0. Okay, because our function is defined as 0 there. But from 0 to pi we have sine of x, okay? Yes. So now we will define this integral from 0 to pi of sine x e to the negative I n x as our integral I, let's call it I, okay? And now if we evaluate it using the tabular method, which can be shown here. If you don't know about the tabular method, I really advise you to look it up on the internet. It is really efficient and useful. This method allows us to evaluate our integral. So once that is done, you should get that result. So 1 over 2 pi times sine of x e to the negative I n x over negative I n minus cosine of x e to the negative I n x over negative n squared, evaluated from 0 to pi. Plus 1 over 2 pi times the integral from 0 to pi of sine x e to the negative I n x over n squared dx. And here you can notice that this, so this comes from the last part of the tabular method, the thing that you couldn't evaluate. And if you notice carefully, this here is our original integral I divided by n squared simply. Okay, it's the same integral sine of x e to the negative I n x from 0 to pi, but there is n squared. So using that, we can do a bit of algebra. We know that our integral here is equal to that stuff here and that stuff here. So if we can take this I over n squared, so this integral over n squared on the other side, and we can factor out the I. Okay, first we have I is equal to this stuff here. Let's call it, I don't know, Q is equal to Q plus this stuff here, which is I over n squared. So now I can take this I over n squared on the other side, and so I can factor out the big I, which is my original integral, okay, which is equal to Q. This Q is this stuff here. Okay, I can multiply by 2 pi here, here, and here, okay, on both sides to eliminate these 2 pi's. So the first thing we are doing here is trying to evaluate this integral sine x times e to the negative I n x, okay? We could also simply use the formula that sine of x is equal to e to the I n x minus e to the negative I n x over 2i, and so we have 2 exponents, and we could evaluate it more easily, but we won't do that here. So now we can factor out this I here, and you're left with 1 minus 1 over n squared is equal to, if you evaluate this whole thing here, the integral from 0 to pi of sine x, something that will be 0, because sine of pi is 0, and sine of 0 is also 0. So this whole thing vanishes, and we're left with this part here, which evaluates as negative times negative 1. Okay, so if you plug in pi here inside this cosine, you get negative 1, and you have another negative sign here, so you get negative 1 times this e to the minus I n x. So if you plug in pi, you get minus 1 to the nth power over this negative n squared. Plus, so you have this 0 here, and it's minus because it's the bottom limit, okay? So we are, if you plug in 0 here, we get 1, and here we also get 1, you have our negative sign here or negative sign here, and we, as said, we get the negative sign because we this is the lower limit of our integral. So if you plug it in, we need to put the negative sign in front of it. Okay, so we're left with this 1 over negative n squared. Now we can rewrite it, so we get negative 1 to the nth power over negative n squared plus 1 over negative n squared. And so yeah, now we know that our original integral times this 1 minus 1 over n squared is equal to this result here. So we can divide the whole thing by 1 minus 1 over n squared to get our original integral. Okay, we can divide by that thing here. And this 1 minus 1 over n squared can be written as n squared minus 1 over n squared. Okay, if you multiply this 1 by n squared on top and bottom. And so now, if you divide again, this n squared here will come on the top on the other side, and so this n squared will cancel with this n squared and this n squared. Okay, if you divide, remember a over b divided by c over d is equal to a times d over b times c. Okay, and so if I divide by this n squared here, this is basically our d, it will come on top, okay, on the other side. And so yeah, the n squared will cancel each other out, and we will be left with n squared minus 1 in the denominator. Okay, and of course the minus 1 to the nth power plus 1, and we will have a minus 1 here, which is the negative sign in front of the n squared. Okay, and so at the end we will be left with minus 1 to the nth power plus 1 over 1 minus n squared. And so now we can evaluate our complex coefficient. We know that the complex coefficient is equal to our integral I, big I, capital I, over 2 pi. And so this is simply the same result as here, over 2 pi. So minus 1 to the nth power plus 1 over 1 minus n squared over 2 pi. And that gives us 0 if n is odd, okay, because if you plug in like 1 or 9 or whatever, we get negative 1, and you have a positive 1 here, so you get minus 1 plus 1, so 0. And if n is even, we simply get 2 here, okay, like if you plug in like n is equal to 4 here, we get 1. Okay, so 1 plus 1 is 2, and you have a 2 here in the denominator, so they cancel each other out, and you're left with 1 over 1 minus n squared times pi, okay? And again, here we need to check the values for n that are not defined. Like if you plug in here 1 or minus 1, we get something divided by 0, okay, because you have 1 minus n squared in the denominator. So if you plug in 1 or minus 1, we get 1 minus 1, so 0. And so we divide by 0. And so we need to check those cases separately, because otherwise those values are not defined for n is equal to 1 and negative 1. And so you can do that. You can just plug in 1 or negative 1 instead of n in the original integral. You don't need to do all the stuff with the factoring out the capital I, okay, because now you don't have something with n, you just have your original integral. And I really advise you to use the formula sine of x is equal to e to the ix minus e to the negative ix over 2i for this case. It makes things a lot simpler. Yes. So replace the sine of x with this e to the ix minus e to the negative ix over 2i. Okay, and here we plug in n is equal to 1 or negative 1. You need to do both cases, and then you evaluate the integral, okay, from 0 to pi times 1 over 2 pi. And you will get your c sub 1 and c sub negative 1. So you should get minus I over 4 and I over 4, okay? If you do that correctly. Now you can find the real Fourier series coefficients. So a sub n is equal to c sub n plus c sub negative n. So we simply get 2 over 1 minus n squared times pi, okay? Here if you plug in first n and then negative n, because n is squared in the denominator, it doesn't change anything. And we add both results, so we get simply 2 times this result here. And b sub n, will simply be 0. Okay, b sub n is I times c sub n minus c sub negative n. And so we have, as I said, because this is squared here in the denominator, this n squared, that we have n or negative n, it doesn't change anything. But here, because we subtract the second result from the first one, and because both are, as said, the same value, have the same value, we get 0, okay? You can just plug in the n squared here, a negative n squared, and you will see that you get the same thing. So if you subtract one from the other, you get 0 at the end. And here you need to be careful, because we don't need to find our a sub 0 as usually. Okay, we don't need to find our a sub 0 or c sub 0, because this 1 over 1 minus n squared times pi is totally defined for n is equal to 0. Okay, if you plug in n is equal to 0, you get simply 1 over 1 times pi. So this is not something divided by 0. This is not something like 1 over 0 or whatever. So we don't need to do the case for c sub 0 or a sub 0, okay? But you need to do it for c sub 1 and c sub negative 1, okay? And so we can find our b sub 1, which is equal to I times c sub 1 minus c sub negative 1, okay? Why is it a b sub 1 and not a sub 1? Because the b's are the odd numbers and the c and the a are the even numbers. So 1 here, this n is equal to 1 is a odd number, so it is a b, not the a, okay? That's why a sub 0 is that's why we use generally a sub 0 and not b sub 0, because 0 is even, it's not odd, okay? Yeah, and so if you plug that in, so if you plug in your two values here inside, and you multiply it by I, so you get I times c sub 1 minus c sub negative 1, you get a half, okay? And so now you have your real Fourier series coefficients. So I said the b sub n are 0 except for b sub 1. So this is the b sub 1 here with the coefficient. So the sine of x, okay, sine of x, because it is n is equal to 1 here, okay? So we don't have sine of nx, we have simply sine of x, because it is only defined for b sub 1. And this 1/2 here is our coefficient of the b sub 1. And for the an, when we have this coefficient here, so 2 over 1 minus n squared times pi, and it is the sum from 0 to infinity. Okay, here we can begin at 0, not 1, because as said, for 0 there is no problem, so we don't need to take it separately. There's only a problem for the 1, but the 1 is for the b's and for the a's, okay? So this is our coefficient a sub n, or cosine of nx, okay? And so now remember that this is only defined if n is even, because if it is odd we get 0 at the beginning. So we can replace this n with like something like n is equal to 2m, okay? So we know that n is always even, okay? Because something like times 2 is always even, okay? And so if you can just replace the n with 2m, and so we get the sum from m is equal to 0 to infinity of 2 over 1 minus 4m squared, okay? Instead of this n squared, we have 4m squared, okay? This is because 2m squared is 4m squared, times pi times cosine of 2mx, okay? Again, you just have 2m instead of n, plus 1/2 sine of x. It doesn't change, okay? And so that is our final result, okay? I hope it was clear, that you understood something. So as usual, the same thing, use the tabular method, the complex Fourier coefficients, and then you find your real Fourier coefficients. Check the values for which your abstract series is not defined. Okay, here it is for n is equal to 1 and negative 1, so you need to check them separately, but you don't need to check n is equal to 0 separately, because it is totally defined. We just get we just get 1 over 1 times pi, so we don't get something divided by 0, so it is totally fair to do it, okay? Yes, and yeah, use this sine of x is equal to e to the ix minus e to the minus ix over 2I for the c sub 1, the c sub negative 1 here, okay? Because if you do it like we did before, you run in some troubles, if I remember well, like the terms cancel each other out and you're left with nothing, if I remember well. So you need to use this formula. I think you should use this formula. You're even forced to use it. I don't think there is another way of doing it, but I'm not sure. Yes, and so remember for the abstract part. So if you have the n here, remember what we did. We set this part equal to our capital I, which is our integral, and we notice that after several manipulations we get the same integral back here over n squared, and so we can do some algebra to solve for original integral, okay? And we can factor out our original integral times 1 minus 1 over n squared is equal to the other part here, and so we can then solve for our original integral, okay? And so then we can find it, and then we can find our complex Fourier coefficients, because we know that those are simply equal to our original integral over 2 pi, okay, which was said at the beginning. Yeah, so I hope you could read something, that it was clear, and yes, thanks for watching.